I'm Renellys Perez, and I'm going to be telling you about PHOD's contribution to the Tropical Atlantic Observing System. We're involved in collecting a lot of ocean and atmospheric measurements in the Tropical Atlantic using a wide variety of platforms. And these in situ measurements are also helpful for satellite CalVal and model validation. Over 200 of our recent publications are focused on the Atlantic, 43 on equatorial or tropical Atlantic, and 28 on Caribbean or Atlantic wormhole science. This work is done in collaboration with our partners. This includes US non-NOAA partners, partners from the Caribbean, the Americas, Eurasia, and Africa. And these collaborations include research collaborations, providing ship time, and data sharing. So a lot of our innovative climate science is focused on the question, how does the coupled ocean-atmosphere system affect sea surface temperature? Specifically in that white encircled region, what is controlling sea surface temperature variations? But underlying that is the important societal question, how does that SST variability impact climate and society? You tend to have Amazon droughts and record hurricane activity when temperatures in that white encircled region are high, and you can have severe Amazon flooding when temperatures in that region are low. We're also interested in improving on the short-term weather forecast. So we want to provide observations for improving hurricane forecasts. And we do that by providing real-time data in the main hurricane track development region, which is shown in gray. And this is an example of observations from September 2019. By having long-term observations, we're able to detect ecosystem changes. The tropical Atlantic oceans are becoming more anoxic or low in oxygen. And there's an increased sargassum threat to fishing and tourism in the Caribbean. With partners, we are out there collecting sustained observations, programs that you've already heard about, the XPT program, Parada, Drifters, and Argo. But we're out there, we're also making developing new projects like the Hurricane Glider project and a current study in the tropical Atlantic. From that, we have science results. So during a positive phase of the Atlantic meridional mode, when you have warm temperature anomalies in the tropical North Atlantic and more hurricanes, we found that that tends to follow a canonical El Nino or traditional El Nino, but not a Central Pacific El Nino. During the negative mode, rainfall anomalies shift southward, and you can have extreme flooding in Northeast Brazil. While there's an inverse relationship between Amazon rainfall and SST, there's a nuanced relationship, and it depends on winds and ocean dynamics. So in 2009-2010, there was an extreme wind event, which caused sargassum to be advected into the tropical Atlantic. Sargassum has grown in that region due to favorable environmental conditions and is annually advected into the Caribbean, creating a regime shift. We have a new study called TACOS, where we resolve the upper ocean velocity structure at 4 North 23 West. We observe energetic velocity fluctuations, which we found drives mixing and turbulent cooling. And it's hard to make those measurements, but it's important because you need it to close the surface nuclear heat budgets and predict SST. It's also important to have those observations because a lot of coupled models have temperature biases in the eastern tropical Atlantic, and those warm biases can be due in large part to having weak mixed layer cooling and entrainment in the ocean, and more joint model studies are needed. We also want to have accurate weather forecasts. Studies have shown the importance of surface atmospheric measurements from buoys for improving weather forecasts, and subsurface temperature measurements and salinity measurements from gliders for improving hurricane intensity forecast. And that example is showing you improvements to the intensity forecast during Hurricane Gonzalo. On the long term, we want to capture trends and shift changes in the Atlantic. The Atlantic is becoming more warm. We have increased tropical cyclone heat potential, reduced wind shear, and that is a more favorable environment for more rapid intensification of hurricanes. We're also interested in areas like river outflows, where salinity stratification is important for reducing cold SST wakes and creating more favorable conditions for rapid intensification. So if you include salinity, your forecast could be more accurate. More and more, we're taking research into observations. We're creating products like eParada, which takes daily Parada measurements. It fills in the gaps with supplementary data and produces estimates of mixed layer heat budgets, and we make all of those estimates publicly available. We also produce maps of the available ocean observations for hurricane field operations, and we do that using the Ocean Viewer tool shown there. Because we have all of this real-time data, when a hurricane passes over a mooring, we have estimates of how it impacts the ocean. So when Hurricane Helene passed a Parada mooring, it cooled SSTs and set off a series of inertial waves that you see in the velocity data there. We started producing weekly sargassum inundation maps for the Caribbean and the Gulf of Mexico, and that provides us an idea of at-risk areas for sargassum. Thank you for allowing me to give you this very quick tour of our tropical Atlantic research, and our next speaker is Dr. Sankili.